This is the second video lecture for Chapter 3 Mendelian Genetics. In this lecture, we'll be talking about probabilities, binomial probabilities, chi-square analysis, and pedigree analysis. In our previous lecture, we left off talking about how you could use the forked line method to answer genetic problems and calculate probabilities of either genotypes or phenotypes. In today's lecture, we're going to start and expand upon this and talk about how probabilities can be utilized in genetic problems. So the basic probabilities are utilized when we calculate likelihood of inheritance. The two basic probability rules that we'll be utilizing are the product rule and the sum rule. So in the product rule, it says, okay, if we have two or more events, and they're independent of each other, then we can combine the probability of one event and the probability of another event to equal the product of their individual probabilities. So we multiply the probabilities. We did this at the end of the last lecture when we calculated what was the probability of being green and round. So a lot of times when we see these ands, that's a giveaway that we need to use the product rule. For example, let's say that we have a penny and a nickel, and we want to know what's the probability of tossing a penny and getting a heads and a tail. Okay, so with two coins, what's the probability of getting heads or tails? Well, we could write those out. So let's say the penny, we get a head, the nickel, we get a head. There's a 1/2 probability of the penny landing on heads, 1/2 probability of the nickel landing on head. That would give this 1/4 of the time we would end up with this, 2 heads. Okay. The probability of the tail being on the penny and the nickel having heads is 1/2 and 1/2, so that's also a 4th. Probability of there being heads on the penny and then tails on the nickel is 1/4, and the probability of both having tails would be 1/2 and 1/2. Multiply those together, 1/4. So here we're using the product rule. Now the sum rule is saying what's the probability of one event occurring or another event occurring that are independent of each other. In this case, we're going to add the probabilities. So let's say we wanted to ask this question. What is the probability of getting 1 heads and 1 tails? Now, you may be saying, hey, Dr. Smith, you said if it's and, it's the product rule. But really, when we have this and here, what we're asking is, what's the probability of flipping 2 coins, and out of those probabilities, one of the coins has a head and the other one has a tail. There's 2 probabilities. If we come back up to here, you saw right here is a probability, right? The tails is on the penny and the nickel's on the head. Or the other probability, and this is where that or comes in, the other probability is if the penny has the head and the nickel has the tails. So what's the probability of this or this occurring? These 2 independent events. In order for us to do that, right, we calculate out, first we'd use the product rule to calculate out what the probability of that event is. We have the probability of this event, and then we would say, okay, what's the probability of those, either one of those occurring? So 1/4 plus 1/4 is going to equal 1/2. So 50% of the time, we will end up with 1 head and 1 tail when we flip 2 coins. So let's look at an example. Mendel crossed peas having round seeds and yellow pea pods with peas having wrinkled seeds and green pea pods. All the F1 plants had round seeds with yellow pea pods. How many of the peas are expected to be either wrinkled and yellow or round and yellow? Okay, so there's a lot to unpack here, and it can be confusing when we first read this. Let's go through our steps for solving and see what we got there. So first things first, how many traits are we dealing with? So if we look here, we say, okay, we have round seeds and yellow pods. Okay. And then we have wrinkled seeds and green pods. Okay, so what we have is, it appears round or wrinkled, and we have yellow or green. So 2 traits, right? How many phenotypes do we have? Well, there looks like there's potential to have 4 different phenotypes. What do I know about these traits? Did I do anything about dominance and recessiveness? Well, yes. It says the F1 plant had all round seeds and yellow. So it would appear that round and yellow are the dominant traits. So I'm going to now give some designations here. I'm going to say big W equals round, little w equals wrinkled. And again, I'm using the letter of the mutant, right? And then I also have big G equal yellow, little g equals green. Now the next part, what I need to do is, what is it asking me? Well, it's asking me to find out something about the offspring. And then I should go and I should look for words that are like and or to try to see. So how many of the P's are expected to be either? So either kind of lets me know that this is an or, right? They're either going to be wrinkled and yellow, or wrinkled, round, and yellow. So I have both a product and a sum rule that I'm going to be applying in here. So now we go to, let's start breaking this down and figuring out what we have. I don't know necessarily what the parentals were per se. I'm assuming they were true breeding, so we could figure that out. In fact, they had to be true breeding. But let's just start with the F1, right? If we assume the parental, so P1, were true breeding, round seeds with yellow pea pods crossed with wrinkled green, this would yield in the F1, because only one type of gamete can be made, so we would have heterozygous individual, which would all be round with yellow. Okay. Now, I left something off here. This should be in the F2. That'll make it a little bit more sense for our problem if this is in the F2. Okay, so now if I do this for the F2 generation, what am I going to get? Well, let's do this forked line let's do this forked line method just to refresh ourselves. So again, I'm going to start. I'm looking at phenotypes, so I'm not going to be doing genotypic ratios. I'm going to be doing phenotypic ratios. So I want to look for first whether I am round or wrinkled, right? This would be W, that, this would be this, and what's that probability? So I can solve that by doing my Punnett square. And again, they're heterozygous because I can see that right here. Right? Which is going to give me that 3-to-1 ratio phenotypically. So I know this is going to be 3/4 will be this, 1/4 will be that. And then I'm going to draw my lines to go to the next trait. For my next trait, now I'm dealing with being either green, yellow, or green. Which again, this one would be G, it doesn't matter what the other one is. It could be homozygous or heterozygous. Here I have to be homozygous small. Okay, what are those? I would do the Punnett square again. The parentals again are both heterozygous. So I should get the exact same ratio of 3 to 1. So 3/4 is 1/4. 3/4 times 1/4. Okay, now I want to go back to my question. It says, what's the probability, or how many of the peas are expected to be wrinkled in yellow? So here's my wrinkled in yellow. So wrinkled in yellow is equal to 1/4 times 3/4, which is 3/16. Okay, the other thing is round in yellow. So round yellow is going to be equal to 3/4 times 3/4, which is equal to 9/16. Okay, but it says either wrinkled yellow or round yellow. So it's either this or that. So now I need to add these. Remember, when we add fractions, we need to make sure that they have the same denominator, which in this case they do. That's why I like to not reduce my stuff till the very end. So I can take 3/16 plus 9/16, and that's going to equal 12/16, which I could then reduce down by 4. So 4 goes into 12 3 times. 4 goes into 16 4 times. So 3/4 of all my offspring will be either wrinkled in yellow or round in yellow. That's my answer. Lock it in, submit. Okay, so here's a great example of how we could work through this. Now, I want to point something out on the forked line that I didn't necessarily point out on the last one, but I want to point it out on this method. This works for both phenotypes and genotypes. The ratios could be a little bit different. So right here, I was doing it for phenotypic ratios, whether I'm round or whether I'm... So this can also be used for genotypic ratios. So instead of saying wrinkled yellow, round yellow, once I said, just the question was, what is the probability of being this? Okay, we could calculate this out in the same way. Really, I don't even have to do a forked line method. I could just do the probabilities right off of these. What's the probability being this? What's the probability being that? And do those two probabilities, use the product rule, and I could get the answer. But I just want to show you the forked line method real quick of how this works for genotypic frequencies. Because so far we've just talked about phenotypic. So here I'm going to do the same thing. I could be this genotypically, this genotypically, or this. And I treat the traits just as the same thing, use the Punnett square, and now I have a different ratio. I don't have that 3 to 1, I have the 1 to 1, right? 1 to 2 heterozygous to 1 phenotypic heterozygous or homozygous recessive. So this is 1/4, 2/4, 1/4. And then when I draw my arrows, this time, again, I'm going to draw 3 because there's 3 genotypic outcomes that I could be for the second trait. I could be big G, like heterozygous little g, or little g. And you would copy this for each of the forks. Sorry, space is getting a little tight. But then what's the ratio here? Again, I have already done the Punnett square. 1/4 would be this, 2/4, 1/4. And this would repeat down, right? Because it's the same thing. So what's the probability of being this and this? Well, here's the probability of being heterozygous, 2/4, or I could have written that as 1/2, doesn't matter. What's the probability of being, so here, and then it's this individual right here. All right, so 2/4 and 1/4. Two 16ths. Okay, I could have left this as 1/2 with the product rule. You can multiply fractions with different things. It's going to give me the same answer. Equal 1/8. If I reduce this down, 1/8. Okay, so that's how you use the forked line method for the genotypic. So make sure you know, is it genotypic or phenotypic ratios? Okay, moving on. You'll start to do, as you do more and more of these problems, you'll recognize that there's important ratios that you start to memorize or recognize. When we're doing crosses that involve an individual that's homozygous dominant versus homozygous recessive, the phenotypic ratio is always 4:0, everybody being dominant. And then the genotypic ratio is everybody's going to be heterozygous. Okay, the ones that we've been doing a lot of are these heterozygous, 2 heterozygous individuals. You get that phenotypic ratio of 3:1. So probability is 3/4, 1/4. And genotypic ratio is 1:1, right? 1/4, 1/2, 1/4. But if you have a heterozygous and a homozygous recessive, you get this 1/2, 1/2 phenotypic probability. And you get a 1/2, 1/2 over here. So a 0, 2, 2. Opposite way if you have this. Okay. The other one you'll notice is when we do a dihybrid cross, if we're doing 2 complete heterozygous individuals, we get that 9:3 to 3:1 for the phenotypic ratio. The genotypic ratio is also 9:3:1, but it gets really complicated on this aspect of it. All right, let's try a different type of problem that we can solve with probabilities. Say we're given an individual that is heterozygous for trait A and trait B. How many different types of gametes can be produced? How do we solve this? Well, you could try to write it out. You could say, okay, he could produce a big A with a big B. You do a big A with a little b, a little a with a big B, and a little a with a little b. That's not that hard because we're only talking about 2 traits. But there's a probability that we could utilize to solve this. What happens if it's this? Well, that becomes a lot trickier. There's a lot of combinations that we could make. In order to solve that, we can use this equation, 2 to the n, where n identifies the number of heterozygous gene pairs that are present. So in this case, how many heterozygous gene pairs do we have? These ones, 1 is heterozygous, 2 is heterozygous, the C is heterozygous, D is heterozygous, and the E is heterozygous. So they're all heterozygous. So this is 1, 2, 3, 4, 5. So I could do 2 to the 5th would give me my answer, which is what? 2 times 2, 4 times 2, 8 times 2, 16 times 2, 32. And you see, we can start to calculate those out. Okay, so the number of different types of gametes can be formed is 2 to the n. The number of types of genotypes produced when we have crosses between organisms would be 3 to the n. So let's practice a couple of these just with the genotypes and the gametes. So here's our ones. How many different gametes can we have? So let's write these out. So the first one, okay, if we count these 2 pairs, it's 2, so it should be 2 squared, which is what we see, right? For B, how many of the pairs are heterozygous? Only 1, so it should be 2 to the 1. For C, how many are heterozygous? 3, so it should be 2 to the 3rd. What is n for D? So only 1. All right, so 2 to the 1, so we get 2. Those are the only 2 outcomes. E, how many of the pairs are heterozygous? N is 2, so 2 squared, 4. Finally, for F, how many are there? That's the one we just did. N to the 5, 32 different combinations of genotypes. Let's give an even trickier question. What is the probability of a family of 7 having 5 males and 2 females? This question now is getting into what we call binomial probabilities. You may remember binomial probabilities from high school, from math. This is where you have a binomial is where you have A plus B and then it's to a power. Well, in this case, we're doing an A plus B to the 7th power. And if we expand that binomial, we get all of these different coefficient effects. And you could use Pascal's triangle to identify what the coefficient is. So if you notice, Pascal's triangle tells us what we'd expect these to be. So when we're at a binomial 5, you have 1, 5, 10, 10, 5, 1, which is what we see. 1, 5, 10, 10, 5, 1. And it just kind of expands and it goes up each time. 1, 2, 3, 4, 5, 6. This one, goes on a different schedule, on a different binomial thing. We can calculate this out. And we can use this binomial probability to answer this question. Now, you may say, how? Well, let's look at this. We're going to need to use factorials and the Pascal's triangle. So the probability of a family of 7 having 5 males and 2 females. Now, we could solve this just by using Pascal's triangle and looking at it to the 7th power and looking at what those coefficients are. But if we don't have the Pascal's triangle sitting right in front of us, we can use factorials to calculate that out. And the equation for that is this: n factorial divided by s factorial t factorial, where n is the total number of events, s is the number of times outcome A occurs, and t is the number of times outcome B occurs. So let's go through this. What do we do? Well, in this case, that probability is going to be n. This gives us the coefficient that we need before our number. And then we'll actually have our binomial problem, which will be a to the s, b to the t. What is the number of outcomes that we're looking for? We're saying a probability of a family of 7. So it's going to be 7 factorial over the probability or the number of times outcome A occurs. Outcome A will be male, outcome B will be female. So 5 males, 5 times 2 females. So 7 over 7 factorial over 5 factorial times 2 factorial. Now, factorials just basically mean you calculate this when you have a factorial. It's 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay. We can cross some of these out. So like literally we could take this and we have that same thing here. So really it's going to be 7 times 6 divided by 2 times 1. That's factorial. You can type this into any calculator that has a little exclamation point and it'll do all this multiplication for you if you've forgotten this math. Okay, now this part right here, this A S to the T, we're going to come back to that. So just kind of disregard that for right now. But when we do this 7 times 6 divided by 2, what we get is 42 divided by 2, so 21. 21 is the number coefficient that we could have found if we had all of Pascal's triangle, right? In fact, right, we look right here. There's the 21. Okay, so what this would be, if I was writing this out, we would have had A to the 7th plus 7 times A to the 6th and B to the 1st plus, and then we get to our 21. 21 of a to the 5th b squared, which that's the one we're actually looking for. So if you come back here, you can see we're looking for a to the s, b to the t. What was s again? Well, that was 5. So a to the 5th and b to the t was 2. So we're looking a to the 5th, b to 2. Now you may be asking, but what is a and what is b? Well, a and b is the probability of that event occurring. So what's the probability of being male? 1/2, right? What's the probability of being female? 1/2. So we're looking for this equation, 21 times 1/2 to the 5th, 1/2 squared. Now, because these are the exact same, we can combine these together. We can add this, so it's actually, 21 times 1/2 to the 7th. When we do that, what we actually get is this probability. 21 divided by 128. That's the probability that if you have a family with 7 children, that 5 will be male and 2 will be female. Okay, this equation could then be expanded. I just asked males and females, but now let's say we gave something in which there's a trait, a probability of something occurring. So we have a dominant recessive trait. What's the probability of being male and homozygous dominant? What's the probability of being female and heterozygous? Well, that would be 1/2 times whatever the probability is of being homozygous, whatever the probability is of being heterozygous. So you can see how you can start answering factorial or binomial problems using these probabilities. Okay, the next probability aspect that we want to talk about is the chi-square analysis. We use chi-square analysis a lot in Mendelian genetics. We also use it in population genetics. And what a chi-square analysis is we're evaluating the influence of chance on genetic data. So are the results that we're getting, did we just get those results by chance, or are they actually what we expected? We take what is observed and we compare it to what we would expect given a probability state. Now, we could have chance deviation from expected. Why? Well, you could have, there's a chance event that subjects are going to have random fluctuations, or sometimes the expected outcome can be diminished. It is diminished if we have a really large sample size. So the larger the sample size, the more that chance gets diminished. So the two outcomes or factors in analyzing predicting genetic outcomes is going to be, one is there true independent assortment? Are the two traits or the things that we're looking at, are they subject to random fluctuations due to chance deviations or not? And then 2, what's the sample size? The larger the sample size, the smaller the deviation. When we do a chi-square analysis, we generally develop a null hypothesis. So the null hypothesis says it's going to assume that data will fit the given ratio. So in this case, we'll say there's no difference between what's measured or observed versus the predicted. So we say observed equals expected. Okay, that's the null hypothesis. And then we apply this, what we call this chi-square, this goodness of fit, to that null hypothesis, and we do an analysis of our observed versus expected deviations. And we can use this for our genetic data. This is exactly what Mendel did. So let's look at a monohybrid cross. Let's say we're looking at an individual that is a crossing that's heterozygous. Okay, and we want to know, is it actually truly heterozygous? So we would expect, if this trait is behaving Mendelian, that we would have this ratio, 3/4, 1/4. Okay, that's what we expect. Now, let's say out of 1,000 individuals, we have 740 that are the dominant phenotype and 260 that are the recessive. So we can now use the chi-square analysis to look at this. And this is what chi-square, this is what the equation actually is. It's the sum of observed minus expected, okay, divided by our expected. So we square this, divided by expected. Okay? So, and remember, it's sum. So let's take it for each one of these. We're going to first do for the dominant. So we have 740 minus 750, which is negative 10. We square that, which is 100, divided by our expected. So divided by 750 gives us 0.13. But we need to add that then, because this is the sum. So we add it to the next one. So 260 minus 250 is positive 10 squared, also 100. Now divided by 250 is 0.4. Add those two together. Our chi-square value is 0.53. Okay. If this was a dihybrid thing, we would expect 9331. Let's say we had these observed the same way. 587 minus 567 squared divided by 567, and we add these up. Here we get a chi-square value of 4.16. Now these p-values are then associated with what's the probability that this is, you could have a chi-square value that small just by chance. P-values, I will either give you the p-value or you will calculate the p-value using a table. Like here, typically calculate your p's by using your degrees of freedom. The degrees of freedom for a chi-square analysis is n minus 1, where n is the number of different categories. So in our first one, it was a 3 to 1 ratio. We just had dominant and recessive. So our n is 2. So degrees of freedom is 1. And you have different, like looking at a table, say you're looking at a degree of freedom, and the probability that we usually utilize is something like 0.05. So at 1 degree of freedom, we'd go across and you'd see, okay, 3.84. That's the chi-square value that if we are larger than 0.384, we would reject the null hypothesis. Okay, our chi-square value was very small. It was 0.53. Okay, that is not a rejection. Our probability would be less than 0.05, which is what it actually is. Now, I'm not going to give you one of these where you actually go across and find it, but general rule on these chi-square problems that I ask you to do, I will give you the critical value. So I would say, hey, you have a critical chi-square of 3.84. You would then calculate your chi-square, and then if your chi-square value, the calculated chi-square value is less than the critical value, then you fail to reject. You say, yep, like it looks like in this case, it's very small. It looks like our observed actually do correspond with expected. There's no random something, it's not going on. These traits appear to be behaving in a Mendelian fashion. Okay. When we have a dihybrid cross, now there's 4 different character states that we could be, so our degrees of freedom would be 3. That's going to change what the critical value is. You can see the critical value is actually larger for this one. It's 7.82. That's how you do a chi-square test. Okay, last stuff that I want to kind of go over on how you could use Mendelian is pedigree problems. So you could be given a word problem and asked to construct a pedigree and then perhaps give some expected genotypes from that pedigree. These are probably the most complex of the genetics problems that you can really be asked. In order to understand a pedigree, we need to learn some terminology. So when we do pedigree problems, we use circles and squares to designate either male or female. And if the sex is unknown, we use a diamond shape. Generally, you will fill in those boxes when they are affected. Okay, so like right here, you see how they're shaded. That means the person is displaying whatever trait we're talking about. A single line means that they are parents and that they're unrelated. If the parents were related, you'd put 2 lines. And so what you see is you start getting offspring, and we label these in order. So let me just write one out for you. Let's say you had mother, father, and they have 4 offspring, 2 of which are female, 2 are male. Okay, when we do generations, what we write is we have a Roman numeral here to designate which generations we're talking about, and then we would number. So this is 1, 2, this would be 1, 2, 3, 4. Let's say we had another marriage, and they had 2 kids that were both male. This would then be generation 3, and here is 1 and 2. Okay, sometimes you'll see on pedigrees, if you've given the pedigree, they might say somebody's a carrier. We would denote that by putting a dot in the line. If they're dead, you put a line through it. If they're twins, they would bifurcate like this. The same thing. If they're identical, usually you also put a line between it. That's just some terminology for pedigrees. When you do a pedigree, we can start to see whether traits are autosomal, recessive, or whether they're dominant pretty quickly. So you'll notice when we do these types of traits, if we have an autosomal trait, we tend to see instances in which the trait skips a generation. So here, it's a generation where one of the parents actually has it, but you see none of the offspring do. But then suddenly it shows up down here. That's a good indication that this is a recessive trait, because if it was a dominant trait, you would expect to see it in the next generation. Another clue in is if you have an individual that suddenly has a trait, but neither of the parents have it. That's a pretty good giveaway that that's a recessive trait. Whereas you see in the dominant trait, again, if one of the parents has it, generally there's going to be an offspring somewhere that has it. You're never going to find an instance where you have offspring that display a dominant trait and neither of the parents has it. So let's do a pedigree problem together. It says Tay-Sachs disease is an inborn error of metabolism that results in death, often by the age of 2. You're a genetic counselor interviewing a phenotypically normal couple who tell you the male had a female first cousin on the father's side who died of Tay-Sachs disease, and the female had a maternal uncle with Tay-Sachs disease. There are no other known cases in either of the families, and none of the matings have been related individuals. Assume that this trait is very rare. Okay, this is an important thing. When we say we assume this is very rare, we're going to assume then that's telling us to assume that Tay-Sachs disease is a recessive trait. And that the chances of somebody being a carrier for it are very, very slow. So the first part of the question says, draw a pedigree of the families of this couple showing the relevant individuals. So let's start. It said that we had female and a male. They are married. Okay? And it says that the male, so on the male side, he had a female first cousin on his father's side. So we're going to start drawing up. We don't know how many other siblings they had. Actually, I'm going to draw this way. So this is his father. And then from his father, said that he had a first cousin, which means this person had some type of sibling. We don't know what that sibling is, so we're going to give it a pyramid. This person obviously married somebody. they had kids, and they had a female that had the disease. Okay, that's a first cousin, right? And not only did they have it, but they also died. Okay, so there could be other siblings, but we're not worried about that. We just drew this. So if I'm doing generations, this is generation 1, generation 2, generation 3. Okay, now on the female side, it said she had a maternal uncle with Tay-Sachs disease. Okay, so here we're going to come over, go up. Here's her father, mother. We're going to go up from the mother. She had a mother and a father. They had kids. And one of those kids was a male who had the Tay-Sachs disease and died. Okay? That's basically the pedigree that we've drawn. Now, what next question it says is calculate the probability that both the male and female are carriers of Tay-Sachs disease. How do we do this? How do we go back? Well, let's going to have to work our pedigree backwards. So we know over here that this person died of it. That means that this individual, whether it was the male or the female, we don't know. Should change this to a pyramid 2. Was a carrier. Had to be a carrier. On top of that, in order for this person, that also means this person must have been a carrier too, because it's recessive. So we have 2 carriers. If this person is a carrier, that means that one of the parents up here must have been a carrier. We don't know which one, but let's just say it was the father. It doesn't really matter. But one of them was a carrier. So now we want to know what's the probability of this person being a carrier and then this person being a carrier on the father's side. Okay, so we're going to assume, because it says assume that the trait is rare, we're going to assume that this person right here is not a carrier. And really I should have just drawn these as, again, all pyramids. Okay, let's assume that they're a carrier. So that means we have somebody that is this crossing with an individual that's that. If we do that Punnett square, you'll see that you have a 1/2 probability of being a carrier. So, what's the probability of this person being a carrier? 1/2. Now, if they are a carrier, what's the probability of the son being a carrier? Again, it says it's rare, so we have to assume this person doesn't have it, that his mother didn't have it. Therefore, we're going to use that same thing. So the probability of the son being it too is also 1/2. So the probability of the son carrying it is 1/2 times 1/2, which is 1/4. 1/4 probability that he's actually a carrier. Now let's go to the mom. Okay, again, going up, in order for this person to have had it and died, both of these must have been carriers. Both parents had to be carried. There's no way you can die from it. No way you can have it unless, because it's recessive trait, you have to be, this person is little t, just like this person is little t, little t. This person had to be big T, little t. This person had to be big T, little t. This is the probability of being little t, or sorry, big T, little t. This is the probability of being big T, little t. So both of these had to have been carriers. So now the question comes is, what's the probability of the mom being a carrier? Well, this is going to be a different Punnett square. And this is where we get to something that's kind of a little bit exciting or tricky. This, when we're doing this Punnett square, can this mother right here be this genotype? Little t, little t. No, that's an impossibility. Why? Because she would have died by the age 2 and would not have given birth to another mother. So we know that there's no chance that can exist. So now our probabilities change a little bit. Probability of being a carrier is now 2/3. It's 1/3 not being a carrier and 2/3 being a carrier. So we have 2/3 here. This is a lethal trait. Now, what's the probability of the daughter having it? Well, if we assume, again, it's a rare trait, the father probably isn't a carrier. So we're going to go back to this Punnett square over here. And the probability of being a carrier is 1/2. So on the mom's side, it's 2/3. And right here, it's 1/2. So times 1/2, which is equal to 2/6. Now remember, the question asked, what is the probability that both the male and female are carriers? So we now have to take both of these probabilities and multiply them. It's a product rule. So 2/6 times 1/4. I could have actually reduced this down. Let's do that. 2/6 is actually 1/3 reduced. So this is 1/12. That's the probability. I answered this question. This is a tricky question. This had a lethal trait. We had to do a pedigree analysis to figure this out. This is as complex as they can come of what I would ask you to do. But you should all be able to do this. You can work through it. Don't be intimidated by the word problem. Just work it down, draw stuff out, do your Punnett squares, and you can get to this answer.